Sure. Thank you very much. Thanks for the chance to speak. And actually, thanks for being here. Let me be here. It's been great. I'm learning a lot. I'm learning that the word unitary is a noun, not an adjective. I've been enjoying my time here because seeing people in action is actually very instructive, and I try to put my finger on why. And I think it's like what we have here, what you have here is like a physics version of an Irish pub, in the sense that lots of fun is going on. And, if every other day a fight breaks out, then, that's part of the fun. So my topic is, and we're in a workshop. I'm in a workshop, UV, IR, and quantum gravity. And so what we haven't heard from yet is the cosmological constant problem, which fits into that squarely, and it also fits into the fight story. And so what I'd like to do is give you an update as to this program. And the program going on is, and not just me, of course, what I'm going to describe is done together with Matt Williams and Ross Diener, and it'll be coming out soon. And what it is it's a statement of where we are. And the goal is, I'm going to start off, so here's the way I want to tell you the story. I'm going to start off with background. I mean, this room doesn't need to be reminded too much about the cosmological constant problem, but what I want to do there is to tell you the problems I'm not going to try and solve. And then I want to also diffuse the self-tuning word, because I think that's probably also one of those words that means a lot of things to many people, and it's not going to mean most of those things in this talk. I'm going to start off with symmetries and how the model is motivated, and that'll lead right to Weinberg's no-go theorem, which is kind of the elephant in the room, which I'm hoping to turn into a virtue. And then I'll tell you about the model, and then I'll tell you kind of where it stands now. And I'd like to be able to tell you that it's working. And my goal this year, I'm on sabbatical, and I've got tenure, so I can spend time on problems like the cosmological constant problem. And my goal was to kill this class of models or to vindicate them. And I haven't accomplished either of those. But I'd say right now, if I had to bet, it's leaning towards the kill side. But it's not. I think there's a way to. What always happens is that you think, the cosmological constant problem is like an argument with your spouse. There's so many ways you can be wrong, and only one way to be right. And so I think there's a way in which this can work, but I could have told you the same thing last year, and that particular way would have been wrong, I now know. So I'll tell you kind of where we are, essentially, and why it looks bad and what looks good and what the hope will be. And then the very last part is general objections to the program, what Randall-Sunder models had a similar thing, and probably we're not going to get there because I was told to make this short and provocative, and this is mostly there so you know that there's a conversation that could be had. And I learned from Joe's talk that a good way to deal with objections is to say that part 3, it'll be in part 3. So, I may not get to part 3, but all right. So what's the program? So the program is, the cosmological constant problem is the one I want to address is technical naturalist story. Technical naturalist is behind a lot of the way we think about physics, of course. And you're supposed to imagine there's lots of scales. We have lots of thresholds in the problem. And the issue will be we've got a small number in our problem, in this case the cosmological constant. And we measure it down at some low energies. And we ask, so it's been measured. That's told us the value of something in our Lagrangian, some parameter. And it was smaller than we thought it would be. And so the problem is not that in itself. It's that when we write down this Lagrangian, traditionally God gives us a Lagrangian, we quantize it, and we go home. But what's the modern point of view is that the Lagrangians are effective Lagrangians, and that there's no unique one. There's different scales have different Lagrangians at different scales. So imagine the cosmological constant, we measured it down here. There's a value it would have above all these thresholds, and they're all related to one another. You get to choose it once. And choosing the numerical size down here where all the scales are the same is telling you that the effective theory down where you're doing the measurement is the one that has the small number. And the puzzle is that as you kind of ask what the number was at higher and higher and higher scales, the number is not just large, it's large in a very specific way that's precisely adjusted to cancel the contribution of the particles that you're integrating out. And that's happening at the level of this is the electron. That's happening at 32 decimal places or 30-something decimal places. If it's a W boson, it's happening at 50 decimal places. How bad the problem is depends on how far up you go. And the part I'm going to focus on is the electron. I mean, the low energy part of it is the hardest problem. Once you're above the weak scale, God knows what's going on. Do whatever you like up there to make it work. But the problem with the cosmologic constant is you're trying to, whatever solves it, the way I'm phrasing it, has to be at low energies. And of course, it's a logically tenable position to say it isn't a problem, to say that there's nothing that forces these constants to not cancel. And I think the only defense against that is history, that we know many hierarchies in nature. We ask how they work. The normal way they work, if you ask why an atom is large compared to a nucleus, normally you can understand that any place you choose to ask the question, and it's not a conspiracy that makes it true just where you happen to measure it. So based on that, it's a conservative thing to ask that this hierarchy be understood the way all the other ones are. And of course, what's spectacular about it is that there's no example of a model that everybody can get behind as being a potential solution. And so that's a bad thing because it means we can't use the clue very well. It's a good thing in the sense that if you find one, it's probably the way nature works. And so there's a lot at stake, and it'd be nice to succeed, but we'll see what happens. All right, so that's the picture. And now I want to specifically argue for a class. Personally, I think I'm going to present myself as if I'm a dispassionate observer, but I really, my heart of hearts, would like these models to be right. And even if the specific model I'm going to give you to test the mechanism is wrong, the class in which I'm looking seems to me has to be where you would find one, if there is a solution. If you're not, I'm kind of putting aside, I should have said when I said that it's tenable to not think that there is a problem, and that kind of leads towards the anthropic way of thinking about the problem. But the class of models I want to think about specifically are extra-dimensional models. And so let me set up why. So I want to motivate the models in the class. And the basic argument is that if you ask what's the problem is that there's something we think should be large, and that's the vacuum energy. We think the vacuum is Lorentz invariant. Quantum mechanics seems to say that should have an enormous energy density. But what we measure to be small is not the vacuum energy. We measure the curvature of space-time when we see the universe accelerate. And so the problem then is that is two things. One is that the stress energy of the vacuum, because of its symmetry, is Lorentz invariant, has just got to be constant times g mu. And then once you stick that into Einstein's equations, then you're basically screwed because you know that this is not any old stress energy. This is such a simple stress energy that it's an obstruction to small curvature, and you're measuring isometric spaces with small curvature in cosmology. And so it's such a simple set of steps that that's what's part of what makes it hard to solve. And so to me, extra dimensions are the only loophole in which you can try and find a solution that seems plausible, and it's essentially changing the assumption that the vacuum was as symmetric as you thought it was. If it's true that you had other dimensions, the vacuum has to be symmetric in the ones you see, the curvatures have to be small in the dimensions you see, but nothing says that the vacuum energy that you see, that should be large, has to be curving what you're measuring in cosmology. It might be curving the other dimensions. And the cartoon of the kind of argument you'd like to have is if you had a cosmic string in space-time, and you ask how it gravitates as a function of the tension of the string, you know that solution, if you solve Einstein's equations, is locally flat everywhere. There's a conical defect kind of at the string. So if you cut a slab out of space-time, there'd be a wedge removed. And when you glue the edges together, that's the explanation for why light rays that go by in a straight line here, where that's supposed to be in the board, one that went on this side would if I drew this from the top with the wedge removed, one light ray goes by, the other light ray goes in, and then it has to come in at the same angle when you glue these things together, and that's how you see that it's gravitating, even though locally the curvature is zero. And in particular, if you're a little two-dimensional person on that string, you'd say, well, I've got a nice flat geometry, whopping big tension, how is that possible? So it's kind of running with that breaking of the link between the vacuum energy and the curvature that this leads you down the rabbit hole I'm about to take you. So that's the starting point. Of course, the reason this isn't a solution in itself is that if I'd done this string in curve space, it would have inherited the curvature of the space it was in. So you have to ask, why isn't there a cosmologic constant in the extra dimensions? And I'd also, even given a cosmologic constant or no cosmologic constant in the bulk, it's not enough to have a solution which is flat. There are going to be other solutions for which the geometry on the string is not flat. And the cosmologic constant question says, you give me the choices of the properties of that string that make it flat, and then I ask, if I integrate out short distance physics, do they stay made, those choices? And so I have to, if I can construct something which does this in higher dimensions, that's the way the question gets rephrased, and so the work is about that, yeah.
Some people say the cosmological constant might be different at different positions in space and different bubbles, different effective field theory. Is your explanation going to apply to all of them, or just to?
Not likely, no. Good. That's the same spirit of that is am I going to kill inflation like if I kill the cosmological constant? That's kind of in time rather than in space.
So it's just us.
Well, as you're going to see, it's actually. I'm not going to, even if I succeed, I'm not going to find that all these solutions are going to be flat. I'm going to find that I can design the properties to make it flat. And in the best case scenario, you'll see that there's a choice I could make for the couplings of a brane, which would make the geometry flat. But if I don't make that choice, they're not flat. And those choices are time dependent if they're
going to show what's connected.
Yeah.
Well, not what.
I'm glad you asked that question because it allows me to make a plug. Is that there's a no-go theorem for finding de Sitter space for inflationary models in supergravities, and I'm going to be doing extradimensional supergravities. And I think the one counterexample to those no-go theorems is in the supergravity I'm going to talk about. And you could ask, why does it evade the no-go theorems? And it evades it for the same reason that it does surprising things for the cosmological constant. So the mechanism I'm going to rely on is something which probably is more useful than just what I'm using it for. That's actually, I should have said at the very beginning. If you said, if you're a skeptic of the whole program, what are you hoping to learn from what I'm going to tell you? I would say it's two things. One is in the mechanics of the whole story will come down to how do you stabilize the size of the extra dimensions. And there'll be new mechanisms that are going to come out of this, which can give you very large dimensions exponentially, much like Randall-Sundrum models, if you like those things. But more generally, I think the bigger lesson is that the class of it's very rare in particle physics and cosmology to find relatively virgin territory, theoretically. And the class of systems for which you look at the back reaction, and back reaction will be an important part of the story, the back reaction of codimension 2 and higher objects, gravitationally and otherwise, is relatively poorly explored. And so sorting through an area that's not very well picked over is actually always fruitful in very mature fields like ours. And I think the cosmological constant problem, if there's a solution, it wouldn't be a surprise to find it someplace people haven't been looking very carefully. But even if you don't, interesting things are likely to be there. And so part of the story here will be why is it true that people haven't done back reaction of codimension 2 or higher objects in more detail, and to tell you how they get solved in the case of interest here. All right. So I've made the motivation that I want to look at next dimension. So the good game will be to try and do something where I've got 2 more dimensions in the string. We'll have 6 dimensions. We'll be localizing those 6 dimensions. We'll make the extra dimensions compact. And there's probably going to be more than one of these sources in general. And I'll, for simplicity, often look at rotationally invariant geometries around those 2 sources. The scales in the problem that you're going to be able to use to try and make a hierarchy will be the size of the extra dimensions compared to the internal size of the vortex, which might be the weak scale. There's a kind of another story that is another talk. The numerology could work if you had this thing be as big as the extra dimensions, as the cosmological constant would want it to be. That's like the ADD scenario. It turns out that it's phenomenologically viable. So but that I say in passing to get across that the L's I have in mind are enormous compared to the normal ones you'd think about for extra dimensions.
Sorry, how enormous? Just
say a micron.
A micron?
Yeah.
But it's how many extra dimensions?
2.
Okay, so that's very like ADD, I guess.
It's very. In fact, I just run the argument backwards. So ADD would have said that we want the gravity scale but the weak scale, and then would ask you then, as a function of how many dimensions, how big they are. This would say, given that you knew the extra dimensions were the size of the cosmological constant, how many of them could there be, and where would the gravity scale be? And if there were more than 2, the gravity scale would be too low. So if this is the way it works, there's 2 of them at most. And so then they also can't be very strongly warped for reasons that will be clear later on. So it's if nothing else, it may not yet be false, but it's falsifiable. And it gives you an organizing principle to think about what should be seen at the LHC and other places, which so far, I'm a happy camper as far as what they've seen. But so the axial symmetry story in practice is going to be, I'm going to use this kind of metric. And so if I talk about B and W as functions, that's what they're going to be. I'll have a maximally symmetric metric in the 4 dimensions, but not necessarily flat. And then we'll have axial symmetry going on in the extra dimensions when I'm being concrete, and there'll be a maximal field in the problem. The model I'm going to try and work with in detail is this one. We have Einstein scalar Maxwell theory, and there's a potential for the scalar. There's a coupling between the scalar and the Maxwell field, And there's two cases I'm going to contrast. The case where this number A is 0, so there's no coupling here, and this is a constant, will be the non-supersymmetric example. That's the kind of the vanilla one that was talked about back in the day by Carl and Guica. And then the supersymmetric version of it will be the same model with A equals 1 and V, this specific potential. And that's the chiral Nishino-Sezgin supergravity. There's other fields, of course, but those other field equations can be satisfied with them being 0, and that would leave this. The thing that's important about the supersymmetric case is that it's got a scale invariance, and that's actually generic to supergravities in the higher dimensions. If I scale a metric by a rigid factor, and I shift the scalar field phi, the dilaton, by a factor, the Lagrangian scales by a factor as well. So that's not a symmetry in the traditional sense, but it's a symmetry of the classical equations of motion. The derivative of the action with respect to the fields is vanishing, and that'll stay vanishing.
Sorry, what is the G here? Is that related to some gauge coupling or something?
Thank you for asking that. That G is a coupling constant for this gauge field. Basically, it's going to turn out to be, and it's a specific one. So there's a lot of gauge fields in the problem. It's a U1 gauge field. There's many in the problem. You could have turned any of them on, but the one that has the special properties is the specific one, which is gauging an R symmetry in 6 dimensions, and that's going to be special because it's got a supersymmetric solution.
So the important thing is that coefficient is not adjustable. Because kappa is the gravitational coupling and G is a gauge coupling, so it's not a free parameter.
That depends.
I guess the vev of phi we could think about.
No, I'd say it's adjustable. I'm going to take it as being adjustable. That's going to more or less be where the hierarchy comes from. So the ungauged supergravities, it would be 0, say.
So that F mu nu is that going to be something that we can see?
Oh, you mean like a 4-dimensional photon?
Yeah.
No. This is in the extra dimensions. It's going to have a value in the extra dimensions. There's a story where it looks like its 4-dimensional partner piece could have been massless, but there's actually an axion I'm not writing down here that gets eaten by it. And there's a Chern-Simons Kalb-Ramon guy going on here, and it has a Chern-Simons piece in its field strength.
And that masses the 4D.
And that gives a mass because of once I turn a background for F, then the corresponding gauge potential shifts, and that breaks the symmetry.
Okay. And
So,
it's not going to matter what the mass is or something? I mean, that's
down the road it might, but it's something. It's not going to play any role in the story I'm going to tell you today. But phenomenologically, you'd like to know, because it is true that there's other, if I've got an axiosymmetric space, there's going to be Kaluza-Klein gauge boson there. And what really happens is that there's a mixing that goes on between, that guy gets a mass too, but the anomaly cancellation mixes it with the one with this guy, and there is a guy, I think it is massless, that's got anomaly-free couplings. So there's a complicated story to tell about the spectrum, but it's not mostly going to play a role in what I'm going to talk about. Good. So that's the Lagrangian in the bulk. I'm going to need to tell you where we live, and so we're going to live on the brain. And there's 2 levels at which I'm going to tell you that story, because when I get down to here, you'll see that I'm going to be forced to be more precise than the first way I'll tell it to you. So the first way I'll tell it to you is I'm just going to say, I have no idea what this thing is, but I'm going to take it as being some defect. I'll do a derivative expansion for its action. I'll take all the coefficients and allow them to be functions of what they can be functions of, the scalar field in particular, and then I'll ask, do any of those choices do anything nice with the cosmologic constant? And then after that, if something works, I'll go and look, can I drive that in a more microscopic way? So these are not going to be in any sense D-brains. They're going to be some object whose phenomenological properties I'm going to explore. And you'll see that the criterion I'm going to get, it's characterized by tension. And most people would stop there. But you're going to see that in derivative expansion, there's a piece with one derivative in it that's going to play an important role. And that's a coupling of this Maxwell field dualized in 6 dimensions will be 4 form. I can integrate that on the world sheet of a 4-dimensional space. And that can have a coefficient zeta. And that has an interpretation which is going to be important, because if we'd done the same thing for a cosmic string, the same things could have happened. I would have had a tension. I could have also had if I was in 4 dimensions with a 2-dimensional string, a Maxwell field in the extra dimensions, or in the 4 dimensions, would have dualized in 4 dimensions to another 2 form, which I could have integrated on the world sheet of the cosmic string. And then this coefficient would have been interpreted as the magnetic flux that was stuck in the string. And so one way to see that is, I should have written it here, but if you, in these kind of pictures where you have a Maxwell field in the extra dimensions, there's a flux quantization condition that n over 2 pi n over g the coupling constant will be the integral of f. If you go through the argument that told you that that was true in the presence of the boundary conditions that come from an action like this with this term in it, it changes so that you pick up a piece on the right-hand side, which is the flux that's localized on those branes. So you get something like sum over the branes of that coefficient, whatever I called it, zeta. And then there's e to the phi appearing because it's basically playing the role of the coupling constant of the gauge field.
Sorry, one more naive question.
Yeah.
In the higher dimensional action, I guess I don't really remember how these supergravity Lagrangians work, but is there not also a bare cosmological constant?
No, thank you for asking that. That's the scale invariance of doing that. It's almost never true that there's a bare cosmological constant. There's sometimes for gauge supergravities there's a potential. Yeah. And so for n equals 8 supergravity, and that potential has a stationary point which is at a non-zero value. Yeah. But there's a shape to it. So and that shape is and one way to see it is that there's generically a scale invariance like this going on in these supergravities at the two derivative level. And so you can have potentials, but you can't have constants.
Yeah, so because in 4D you could, so that's why.
4D you could, yeah. But in 4D with two supersymmetries you couldn't.
Yeah, you couldn't.
And that's kind of more or less what's going on, is that the higher dimensions are like more than.
This is like higher dimension n equals 1 somehow.
Yeah, right. That's important because I'm not going to talk about the quantum corrections, but there's a story there too, which is a different talk. And part of what's making it work is the absence of a counter term, a cosmological constant counter term in the extra dimensions because of supersymmetry. Okay, so I'm getting ahead of myself a little bit. So to flesh out this story, let me tell you now not quite the model. I want to take you through the non-supersymmetric version of this to show you why it doesn't work. There's no magic in the extra dimensions by themselves, and the scale invariance is going to be an important part of the story. So the way to see that is, the reason you think that there might be magic is, the basic reason why when you solve this, the geometry of a cosmic string, the curvature doesn't depend on the tension, is that in a codimension 2 system, the trace reverse Einstein equations has a 1/4 here rather than a 1/2. Mm-hmm. And so what's happening is that in the mu nu part of the Einstein equation, if you have a maximally symmetric stress energy, so that's the mu nu part is proportional to g mu nu, that's canceling here. And so what's surviving is the trace in the extra dimensions of the stress energy. And in detail, if you take this ansatz and put it in the field equations, you find the four-dimensional trace is something like this. There's the four-dimensional trace of the six-dimensional Ricci tensor is related to the induced one, the one for this metric, by the warp factors and a total derivative, and then there's the two-dimensional trace of the stress energy here, which, morally speaking, will be the potential minus the Maxwell term in the extra dimensions. Good. So now...
I'm sorry, that just went by a little fast. Could you say again how you're thinking about that?
This?
Well, the 4 ion, yeah, that I understand. But that equation's supposed to be in 4 dimensions only?
No, this is actually the full six-dimensional equation.
Oh.
And in general, this would have been, if I had a...
But then, yeah.
If I have a codimension, if I have little d dimensional surface and then little d plus 2 dimensions in space-time, this would have been little d, essentially. Yeah. And so in 6 dimensions with 4-dimensional brane, it's a fourth. But in general, d, if you had that d is what you need to take out the trace of the stress energy. So it's always true that in codimension 2, the stress energy is the curvature on the brane is depending on the stress energy off the brane. But so that sounds promising, and that's kind of what motivated models back in the day. But so let me now take you through the argument as to why that's not actually sufficient. And what you do is, the simplest thing to do is to take the simplest case where you take this thing to be very symmetric, to be a sphere. And then what happens is that the back reaction boils down to there's a defect angle, and if you did things so that you had identical things at both ends, then you would have it's like removing a wedge from the sphere and gluing it together, and that would give you a defect angle everywhere. And what you can do is take the contrived case where you just perturb them both in the same way. So you just take the tensions and adjust them and ask how does the system respond. The field, if you count the field, you have a Maxwell field in the extra dimensions, and it has an integration constant in proportion to the volume element. You have the two-dimensional curvature, basically, the four-dimensional curvature. So you have 3 variables, and you have 3 equations to solve. The Maxwell equation just tells you that f is a constant. The 2 Einstein equations tell you what R4 is, and this will tell you how big the extra dimensions are. 2 goes over that. And you can solve them all as a function of the defect angle, it turns out. And so in general, what you find is that this is not 0. It's given by the cosmological constant minus the Maxwell term. So f squared, if I put it in here, it's something times little f squared. And so generically, it's not 0. But what you could do, and what these people did, Carol and Guica did, was they said, well, let's tune this to be 0. And then what they didn't do, but what you can do is say, well, so having tuned this to be 0, let's now change the tension on these branes and not retune the cosmological constant and ask how big is the curvature that you got to see whether or not you've improved on what you would have thought in 4 dimensions. And if you go through that exercise, what happens is that if you change the tension on the brane, so make sure the point is, so f is a function of alpha and the integer and flux quantization. R2 is which is L is a function of alpha, and R4 is a function of alpha. When you solve all the equations, and what we'll do is we'll turn this to be 0, change alpha, and then linearize everything and just track through how R changes. And what happens is that when you change the tension, you change both the defect angle. You make it if you actually make the tension bigger, you make the defect angle smaller. So alpha is 1 minus kappa squared tension over 2 pi. So if you make, and alpha is the thing that would be the periodicity. If I scale this in the angular variable, it's going from 0 to 2 pi alpha. So alpha smaller means a bigger defect angle. So if I make t bigger, alpha smaller, the defect angle gets bigger. But it's also true that L adjusts the size of the extra dimensions, and so if you kind of track those through and ask what changes the curvature, it turns out that it's all coming from this. That as you change the geometry in response to changing the properties of the brane, it's flux quantization that gets you, because you're changing the size of the integration volume, and the integration constant in F then compensates to make the right-hand side not change. And if you track that through, that's the thing that gives you the change to R. And it turns out that the change to R that you find is exactly what it's minus the 4-dimensional Newton constant times the change in tension. Actually, it's twice the change in tension for this rugby ball. This spherical thing I'm talking about. But the 2 is because you had to do it at both ends in the same way to keep these solutions being just spheres rather than being a more complicated solution. So the upshot there is that when you perturb these systems, they don't do anything special. They give you exactly the curvature you would have expected if you just in 4 dimensions added that much energy to your vacuum. So great. So now the reason that, to those of you who have thought about this problem back in the day when it was proposed, probably stopped thinking about it, was you can repeat that exercise in the supersymmetric case. I'm going to argue now that I'm going to focus on the supersymmetric case and ask what happened then if you repeat that exercise here. So the next 10 minutes will be, there'll be a problem, and I'll show you that the resolution of the problem is that people were ignoring this, and that's actually competing with the things that were not being ignored. And so then the supersymmetric situation, the reason that you can find that there had to be something wrong with the original way of formulating the problem will be that there's a general theorem you can prove about the solutions of these equations that I'll tell you. Including this will reconcile everything, all the perturbative calculation with the theorem, but then that'll lead us to the real problem. And so then that'll be the end of what I'm going to say. All right, so that's kind of a roadmap of where we're going. So I'm going to tell you same story I just told you, but in the supersymmetric case, show you what happens, and it's puzzling. I'll show you why this term is actually important for that story, and then I'll show you why that leads you to what looks like a good situation, and then right after that thought, you'll see why there's a potential problem with that.
Did you tell us what the no-go theorem was?
I forgot to tell you the no-go theorem. Thank you. That's actually what I should have said next. So I'm going to first, so before I tell you the SUSY thing, why would you expect it to be different? And so what's going on here, part of what's making the SUSY thing nicer is that it has a scale invariance. And scale invariance thank you for asking, Marty, because that was supposed to lead into this aside as to what can scale invariance do for you and what can't it do for you. So the SUSY case differs from the non-SUSY because of the scale invariance, mostly, at the classical level. So if you remember, so the story of scale invariance goes back to the 80s. If you forget extra dimensions and you say, is there a symmetry I can protect the cosmological constant with? At first sight, there is one. There's obvious ones like supersymmetry, but it has the problem that if supersymmetry only protects the cosmological constant if you don't break it. But we know that we've broken it by an amount that we haven't seen the superpartners. And so that doesn't really solve the problem. But scale invariance is unique in that at face value, you can spontaneously break it and still have it protect the value of the vacuum energy. And that's because if you take a scale invariant potential, let's say 5 to the 4th, you're not surprised that there's a theorem that says for a scale invariant problem, the potential is minimized at 0 because there's no scale in your problem, right? But it's also true that you don't have much of a cosmological constant problem there because all your masses are 0 there too. But imagine that you had more than one scalar field and you arranged the potential, and just take as given that scale invariance was a symmetry and had no anomalies. Then you could imagine spontaneously breaking the scale invariance. So you can imagine if we have a multi-dimensional thing that instead of drawing it this way, I have a trough. So I've got there's a kind of a flat direction. And at this one point, it'll be scale invariance. This is where all the fields are 0. But if I move away from the scale invariant minimum, the fields are not 0. And so masses that, say, Yukawa couplings that saw that VEV could now give masses to particles. What you know about the value of the potential along the bottom of this trough is that it's 0. And that's because, unlike the usual Mexican hat situation, where the symmetry direction moves you around a region which is disjoint from the invariant point, in the scale invariant case, the scale invariance is relating all the scale breaking places to the scale invariant point and out, because you're scaling the field, and the particular case where you rescaled it by 0 is the scale invariant point. And they had to be degenerate because by assumption that was a symmetry. So it looks nice. It looks like you could live out here, break scale invariance, and then all is good because you've got masses, but you still understand why your potential is minimized at 0, and that's because of scale invariance. And then Weinberg's no-go theorem was, he was trying to put the silver spike through all the papers that were being written using that idea, essentially, in the 80s. And his observation was that that's all fine. Let's say give you everything that you want. So scale invariance is a symmetry. There's no anomalies to it. Scale invariance in itself can't protect you from corrections that will lift this flat direction. And if, by giving you a lambda 5 to the 4th in that direction, which is consistent with scale invariance, and then you're back to the problem that you had before, that you have a minimum and it's at 0 for sure, but all your masses were really 0. And so the problem is scale invariance can help, but the generic problem is it can't stop you from lifting the flat direction. And so in itself can't be a solution to the problem, because quantum corrections that are scale invariant will generically do that.
Sorry?
Sorry?
Would you repeat that?
Quantum corrections, even if they're scale invariant, will generically give you this lifting. And they're competing with nothing classically, and the symmetry can't forbid it, so generically it's there. And if what can forbid it is things like supersymmetry. So if one way of thinking about the models I'm taking you through is they're going to rely on scale invariance in an important way classically because the supergravities in the extra dimensions have scale invariance. But Weinberg's argument says nothing about how big this lifting is. And it's going to be true that the scale invariance I'm talking about is not really a symmetry. It's only a classical symmetry of the equations of motion. So the corrections will be much more complicated than just something like 5 to the 4th here. And so the logic of the models is to try and use the sequestering of things in the extra dimensions to keep the standard model away from the things that are lifting the potential. And that's kind of the program as to where you'd hope to go.
And what do you say about the scale anomaly?
Well, in my case, it's not going to be that before you hit the scale anomaly, there's just the fact that it's just not a symmetry. So even classically, it's not a symmetry. Oh. It's a symmetry of the equations of motion, but the action is not invariant. And so what will happen is there'll be corrections, and they will include the one that Weinberg would have allowed, but also other ones that are forbidden by scale invariance. And so the generic question of the lifting of the flat direction is there. Extra dimensional models are giving you this where they generically have spontaneously broken the scale invariance. That's why they have this symmetry. And they're anchoring you to the flat point, which is the flat solution in the extra dimensions. That's kind of why you knew that you were at 0. And that's the thing you're trying to live off of. Okay. So now let's repeat the argument. What happens in the supersymmetric case is you get another field, phi, but another field equation as well. So you might have thought that you can now find everything as a function of alpha and just go through this exercise again, but you can't quite do that because of the scale invariance. The scale invariance says that one combination of phi and the metric is never going to be fixed by the classical equations because of scale invariance, that's the flat direction. So what you find is that there is still 3 conditions on these 4 things, and phi is basically a free parameter that labels where you are on that vacuum. But the 2 interesting things do happen. If you go through the supersymmetric case and you look at what the field equations tell you, they tell you that the right-hand side of the 4-dimensional Einstein equation is vanishing because this is canceling this. And the flux quantization condition is such that the thing that determines the value, whether they cancel or not depends on how big F is, right? And that's being fixed by flux quantization. And it happens that in the supersymmetric case, the flux quantization condition is the one that makes this 0. Just 0, 0. And that was what was observed in the Salam-Sezgin solution back in the early 80s without these branes. And the reason it happens, it came to be realized in the Salam-Sezgin case, is that it happens when the flux quantum is 1. So if n is equal to plus or minus 1, that turns out to be the situation which preserves one supersymmetry of the 6-dimensional supersymmetries. And that's kind of why this is giving you 0. There's a flat direction, and supersymmetry is keeping it flat, essentially. But when you turn on a brane, you break that symmetry, but the supersymmetry, it doesn't immediately hit you in R. But the way you see that there's a funny thing going on is if you ask, how does F, remember what happened in the non-supersymmetric case is you perturb the tension, the geometry responds, and it's an expensive response because it's proportional to the volume of the extra dimensions. But it's coming from the change in the flux. If you ask how that plays out in the supersymmetric case, it turns out that the same thing, the condition that phi be constant, and this term here is not there if you use this Lagrangian. The same thing that's on the right-hand side of the Einstein equation is on the right-hand side of the box phi. And so if you track through what the solution tells you, it tells you that the flux quantization condition becomes n is equal to basically some number times alpha. And so if alpha is not 1, this is n, which is equal to 1. So the number is 1, if you normalize it right. And so it says that you're not allowed to perturb alpha without violating flux quantization. And so that's where people, I think, left this problem, was that it seemed very rigid, that the extra dilaton equation tells the flux, it tells you what the value of the field strength was. And so it can't respond if you try and change the volume by changing what's on the branes.
Why doesn't phi run to minus infinity?
Oh, it doesn't, because so if it had been true that the trace of the stress energy in the extra dimensions had been not 0.
But up there in your original Lagrangian there.
Yeah.
Yeah.
You're thinking that if I turn everything else off, then this is just going to drive the potential off to 0. And what's happening is that if I take the Einstein term and the Maxwell term, the potential term and the Maxwell term, this is basically a number times e to the phi. And then there's a root g.
Okay.
What's happening is that you're getting, thanks for asking this because I wanted to write this formula anyway. You're getting something which looks like the volume. If I think of the radius of the extra dimensions, I guess I'm calling it L. If you go to a 4-dimensional Einstein frame, there's a 1 over L to the 4th, it turns out, when you do that. And then this gives you a 1 over L squared. This gives you an e to the phi, basically. And this gives you an n for the flux quantum times e to the minus phi times L to the 4th. And it happens that the coefficients are such that this is a perfect square. So there's if I pull the e to the phi out, you get e to the phi over L squared. And then you get basically 1 minus n over L squared e to the phi squared. So what's happening is that the energy in the Einstein term, the Maxwell term, and the potential are canceling off. If they didn't cancel, it would have been Weinberg's runaway. You would have had an overall e to the phi. But it is canceling if n is equal to 1 or minus 1. There's a sign here that I chose. And that's because the supersymmetry is making it flat in that case.
Oh, I see.
Okay. So I told you that story to tell you this story. It looks like you perturb the system and it can't respond. That looks like there's going to be some sort of a runaway. That's why you can't find a solution within the ansatz I've talked about. But I want to give you evidence that that's not in itself what's going on. So there's a very general statement that you can make about what the curvature is in this supergravity and actually in all supergravities because of the scale invariance that they share. So in this supergravity, you can see here from the equation of motion for the 4-dimensional curvature and the equation of motion for the dilaton, where this term is 0 for the supergravity. This is something which is all to do with the sources, it turns out. I can take a linear combination which kills those two terms, and then I have a formula which says that the geometry I would measure on the brane normalized in such a way that turns the 6-dimensional couplings into 4-dimensional couplings is a total derivative. There's a piece involving a total derivative of the warp factor, and there's a piece involving box phi. And so that shows you that if I had done the integral of the field equations in the bulk, and I just didn't know what was inside these sources here. I had a very, very small pillbox. I could predict for you what the curvature is in this maximal symmetric geometry completely as a function of the boundary conditions near the sources. And that turns out to be a very general statement for supergravities, even not in 6 dimensions, in 10 dimensions, 11 dimensions. Because of the scale invariance of the action, it's always true that if you evaluate the action at any solution to the classical equations, the action evaluates to a total derivative. And so if you think about integrating out the Kaluza-Klein modes to ask what the 4-dimensional curvature would have been, although in general it could have been that it depended on the details of the solution everywhere in the extra dimensions, in practice, all it cares about is the boundary conditions that solution satisfied at the positions of the sources in any number of extra dimensions, not just 6. In this particular supergravity, the boundary condition that counts is the derivative of the dilaton because of this fact that it's r plus box phi that's satisfying that. So that tells you that if I can arrange a source, so the claim is, if I can arrange a source such that the normal derivative of phi goes to 0 at the source, that's a sufficient condition for the geometry to be flat in the 4 dimensions. And so if you ask, what would that mean? This is the back reaction part of the story. What do I need to do to ensure this kind of a derivative? The way that you solve the back reaction problem, so what we're asking is the question is, I give you parameters for a source, such as the tension and zeta over there, and I solve for what the back reaction of the bulk is, which means there's some integration constants in the field equations, which I'll determine in terms of what you tell me the source did. The problem in doing that generically for codimension 2 and higher is that the fields are all diverging where the source is because it's like a Coulomb potential. It's singular where the source is. So the way you should handle that is the way you would do the Coulomb solution if you were in first year physics. You wouldn't actually talk about the source. You'd make a little Gaussian pillbox around the source, and you'd talk about the flux out of the source. And you can formalize that to say that if you ask about, in 3 dimensions, r squared d potential dr, that picks off the charge in the Coulomb solution in some units. And that's proportional to the derivative of the point particle action with respect to the gauge potential, because that would have been like the integral of a mu dx mu times the charge. That's what the action would have been for a point particle. And so one way of phrasing how the back reaction, the bulk response to the source is what you're doing is you're taking advantage of the fact that there's a hierarchy of scales between this scale and that scale. So you choose a scale in between. That's the far field zone for the source, and so you can use a multipole expansion here. And from the point of view of the outside, to see how things respond, you're just asking for boundary data on that surface. And you can formalize that as the statement that the radial derivatives of the fields as they approach the source are proportional to the various multipole moments if you knew what the brain action was. And so with that in mind, the way you make this true is to have the action be independent of phi. That should be enough to make m dot grad phi go to 0 at the source. And that sounds great, right? If you wanted to have a criterion for the flatness of something which will like to be stable under integrating out ultraviolet modes, that's the criterion. Take all the particles that are dangerous, like the Standard Model, put them on this brane, and don't let them couple to the dilaton. Then loops of them only won't grow a coupling to the dilaton if you didn't start with a coupling to the dilaton. The only thing that will be dangerous will be a loop that makes the Standard Model talk to the metric, which it does, which then talks to the dilaton, which comes back. But now supersymmetry in the bulk can help you with that. So it sounds very encouraging that there's a very general criterion that is sufficient for the flatness of everything, but it sounds also weird that you have that criterion and this simple calculation didn't see it. And so the resolution of that second weirdness is this term. This term wants to contribute to the curvature at the same level. The tension is trying to drop out of the curvature. And this term wants to contribute, and it wants to contribute at the same size, surprisingly because of the derivative expansion. And one way to see why that should have been true in retrospect is, although a generic brane with just tension breaks supersymmetry, I can design a brane which doesn't break supersymmetry. If I was in 4 dimensions, I could have had a cosmic string which was supersymmetric and only broke half the supersymmetries. And if I don't break the supersymmetries, I'm not expecting to get a curvature because my potentials will stay flat. And the way that brane will be a BPS brane, and there'll be a special relationship between its tension and its magnetic flux, which will be a relationship between that and that, which will be sufficient to make the curvature 0. And so the point of the exercise is that Neglecting this is just always wrong because it's trying to compete with this, because that's the way the theory would have known that supersymmetry was giving you a 0 for your potential. And when you put this in, repeat the argument, you can see that it changes because the problem was flux quantization. The system couldn't respond to small changes to the size of the geometry because the flux was rigidly being nailed down by the field equations, by the flux quantization condition. But now there's a piece coming from the branes. So now what you can do is you can move flux from the branes, bulk to the branes, and small perturbations don't make this equation false anymore. And it's not an expensive energy cost because it's not scaling with the energy of the extra dimensions. It's a local thing because it's localized in the branes. And when you work it through, the amount by which you move flux is exactly what you would have needed to make this theorem true. So if you perturb the brane in a phi-dependent way, so you do get a small derivative to phi, the amount you get by that argument is the agreement with the amount you get by this argument. And so the thing that might have made you stop thinking about these models in the 10 years ago was mostly to do with ignoring this thing. So now I'm at the point where I can tell you what's wrong now. Okay. So to do that, let me summarize the point so far. The point is that supersymmetry can do better because it's got a scale invariance going on. It needn't do better. But the way that you will see it respond to small changes in energy will require you to have a coupling of this type between, this is what I call brane localized flux. And it's a direct coupling of the flux that's stabilizing the extra dimensions to the source. That's required to see the small changes in energy. So we need brane localized flux to have small delta R possible. And the sufficient condition for flatness was the absence of coupling to phi. Or is ensured by phi independence. So the question is, are these now consistent with each other? And the reason a year ago I would have said, how can you stop me not coupling to phi? I get to make up what the brane is, and it's going to do whatever it wants. The problem is going to be that the flux that you want to talk to, its coupling constant in the bulk is phi. You can see that because the scale invariant says that another way I could have written this Lagrangian if I'd gone to a frame where the metric had been invariant would have been like this. It's like string theory where you have an e to the minus 2 phi and then stuff involving only derivatives of phi. That kind of shows you that e to the minus 2 phi is the loop counting parameter in the bulk, and in particular for this gauge field. And so then you can kind of see that it's going to be tricky to have a coupling to the flux and not have a coupling to phi. Mm-hmm. So to try and nail that down, this is the other sense of in which under the microscope comes in. The story I've been telling you so far has been deliberately a macroscopic one. I've been trying to ask, what do I need to know about the source to see what the bulk is doing, given that I know the physics of the bulk? And I'm thinking that it should be easy to track how the boundary conditions appear in the bulk physics. But I haven't been so worried about what the details are of that bulk physics. I've been thinking of it as some effective thing and not really worried about the details of where it came from. But to answer a question like whether or not one or two are consistent with each other, I need to do better. And so let me give you a very quick elevator sketch of where that goes. So the way we've been addressing that is to make a microscopic model of the source. So what we can do is we can just make a UV completion for the source, and it will give you now, instead of being in these energy ranges, we're going to now tell you the physics here. I'll tell you LUV, and that's what this Lagrangian is. He said, this one. So I'm just going to make up a vortex, a system that will support a Nielsen-Olson vortex. So it's got a complex scalar, it's got its own U1 field, and it's got to have its own U1 field because a Nielsen-Olson vortex, it likes to have some profile which then localizes all the flux in the profile and not outside the profile, whereas I need something which has flux outside and inside. So the way we'll mock that up is we'll have a Nielsen-Olson vortex which will localize some flux. That's a new U1, Z, and I'll have it talk to the gauge field outside by putting in a kinetic mixing term. So this is the gauge field outside, this is the gauge field inside. And if you've done any of this kinetic mixing, you know that if I have a massive field and a massless field, what happens is that The massless field doesn't grow any new couplings, but the massive one grows couplings to the other field when you diagonalize the kinetic terms. That essentially happens here too. And far from the vortex, what's happening is that the Z is massive and the photon outside is massless. So if I have a test charge out here that coupled originally just to A, or F and N, what will happen is that mixing is going to now grow a coupling between Z and that test charge. And so if I do move that test charge around the vortex, there'll be a Bohm-Aharonov phase coming from Z, a localized component that wasn't there before. And that's accomplishing what this would have accomplished. It's giving you a localized piece to the field strength. And so you can kind of match this solution to that solution, and you can calculate zeta as a function of epsilon. And what I'll do is I'll stick in phi dependence everywhere and ask, can I make it so that there's no phi dependence in this Lagrangian, in this effective Lagrangian, to get what I want, even though I have a flux term. And the short version is you can kind of see that it's going to be hard, because what's happening is you have three kinetic terms. You've got an e to the minus phi f squared term. You've got an e to the p phi z squared term. And you've got an e to the epsilon e to the r phi zf term. And what's going to happen is that when you diagonalize things, you're going to take a linear combination of these things. And the z coupling turns into, once you diagonalize, it gets normalized to e to the p phi minus epsilon squared e to the 2r plus 1 phi. Turns out. And that's so now you can kind of see that it's going to be hard. If you wanted p to be 0, you'd have to have r be minus a half. But if you ask what's the phi dependence of zeta, it turns out that zeta goes like e to the r plus 1 phi. So it's only scale invariant. It's only independent of phi in the scale invariant case. It turns out r equals minus 1, p equals minus 1 is scale invariant case, because that agrees with this minus 1. So the short version of this is that it is indeed difficult to arrange for phi not to have both these things be true together. So why am I not telling you it's dead? If you track through the curvature you get is all to do with the fact that phi is coupling is true, but it's coupling in a way which is proportional to the gauge field in the bulk, and that's all suppressed by the Kaluza-Klein scale. So it's all the Maxwell field is going like, it goes like an integer over r squared, basically, or l squared. And so it's true that you get a curvature, but it's a contribution which is Kaluza-Klein suppressed. And the thing that I'm not sure yet, and the reason I can't tell you whether or not this is going to play out yet, is so the upshot is you get a potential for phi, which you have to stabilize to tell what the radius is, because there's something else I forgot to tell you. One of the equations of motion, besides telling you that the curvature is 0, also relates the radius of the extra dimensions to the value of phi, because they're tied to each other by the scale invariance. You don't know what the radius of the extra dimensions is until you stabilize phi. And so the point of calculating this potential for phi is that once you've found it, you'll minimize it and ask for there to be a minimum somewhere where both L is large and the potential is small enough that the curvature is small enough. And so there's a whole story there which is to do with what does this picture look like in 4 dimensions. And that's my closing note. Is I'll tell you what the picture looks like in 4 dimensions, and because the thing to ask is, why should you think that there can be a way that things can work? And so the story in 4 dimensions, the puzzle in 4 dimensions is always, the physics that's important is the flux quantization. And the question is, how does the 4-dimensional theory know that? Because it doesn't have any fluxes. And the way to sort that out turns out to be in these papers, the hit us reading the old Busso-Polchinski paper, is that the efficient way to write this theory is not in terms of the Maxwell field, it's in terms of the dual of the Maxwell field. And so that's a 4 form. The effective theory in 4 dimensions is simplest if you write it as being, there's an Einstein term, there's a scalar that wants to be light, that's the flat direction. There's a potential that you're trying to calculate, V, but there's also a 4-form field. So there's a 1 over 2 times 4 factorial Z, F mu lambda rho, F mu lambda rho. And then there's a piece in general which is linear in F. So there's a 1 over 2 times 4 factorial zeta, F mu lambda rho, epsilon mu lambda rho. So in that sense, this kind of starts to look a little bit like unimodular gravity, although not exactly. But the story is that you can now match the properties of this theory to the full theory, and in particular, the way that the theory knows that it's got flux quantization going on is that when you calculate the field equation for F, it tells you that F is proportional to, or F, it's zeta times a number plus some integration constant times epsilon. And that integration constant is something you have to fix by matching, and it's the same integration constant that you get in the higher dimensions, because if you do this duality in the higher dimensions, star F is proportional to the integration constant F that's quantized. And so there's a simple quantization story, which is essentially the one in the Busso-Plotninsky story paper, which brings the news of quantization from the higher dimensions to the lower dimensions. And when you track that story through and calculate the potential, the way it seems to play out in this example where you make things as scale invariant as you can is that you get a potential which looks like the piece coming from this potential. There's a piece which looks like 2g squared over kappa to the fourth times the volume. And there's this thing coming from the flux, which is 2 over omega volume, an integer basically up to numbers minus this zeta thing squared. And so if you count the small numbers in the problem, the size of the extra dimensions is going like kappa over g. And so this looks like it's proportional to this is a bulk term, so that's why it's got the volume in it. But it's explicitly suppressed by g over kappa, so this whole thing comes out to be order 1. This looks like it's suppressed by the Kaluza-Klein scale, but it's actually enhanced by this n is really an integer divided by the gauge coupling. So it's actually got a large number. So it's got a 1 over g in the denominator. And if you look at this n squared term and this term, those are the ones that canceled in the supersymmetric case. And so the way this potential is working is that there's a cancellation of the order 1 term going on because the bulk was doing something nice. And the brain is dragging it away from the nice bulk story in a way which is generically Kaluza-Klein suppressed. And what's not clear, so the generic Kaluza-Klein suppression I think is clear, but what's not clear is that it's not a runaway. That the potential, what you have to have is a potential which is it's got some sort of a minimum somewhere which snags you somewhere. And so if you ask me now how I think if this is ever going to work, it will work, the mechanism in 4 dimensions will be that you'll get some sort of a potential which is some series it'll have a small number in it. Say it'll have g squared over kappa squared, and there might be a g squared over kappa e to the phi, and there might be a e to the 2 phi, all times the runaway e to the 2 phi. And the best case scenario, I think, will be that the small numbers that are controlling the hierarchy between the vortex and the extra dimensions will come in such a way that the Weinberg runaway wants this potential to run off to 0. And the way that the potential will make a virtue of that will be you can have a big coefficient of that, but if you can snag it somewhere out here, because you've got some pieces in your potential which are suppressed by these small numbers, then it will automatically be true. 2 things will be true. You'll get e to the phi will be very small, and that's another way of saying the extra dimensions are large. But the curvatures will be small just because you've come way out on an exponential potential to make it small. So whether you can actually realize that in any of these explicit constructions, I don't know. But that's where we stand.
Clifford, are you envisioning that the quantum quantized levels are very close in effective 4-dimensional lambda, or that there's one that happens to be close to 0? That was, as soon as you have this quantized 4-form flux, how is that manifest?
Well, the steps, you asked about the steps in F.
How big are the steps?
They are
Making small steps or big steps?
They're Kaluza-Kleinish steps. They're not small compared to the Kaluza-Klein scale.
So in order to get a small lambda, you need that one step happens to be close to 0.
They're
one
bigger than that,
particular step has to be close to 0.
No.
Level. But you have many vacuum with small lambda, or just one vacuum with small lambda?
1. If I find any, it'll just be 1.
Just be 1. Okay.
Yeah.
So you have.
And so the thing is that I lied to you. The steps are actually bigger than Kaluza-Klein size because they're being set by the gauge coupling, which is actually that's small, and 1 over it is. But the minimum is going to want to be the thing you're perturbing around will be the one that wants to be at 0 but scale invariant. And then I'm hoping that the phi dependence of these. The thing that I'm doing, which might not be obvious right from the beginning, is that in the bulk, the gauge coupling and the phi are always appearing together. So I don't really have a separate small number g squared over kappa compared to phi because I could just shift phi and change g squared over kappa. But I'm not going to do that I'm going to choose the couplings to not have that property, so I'll have this small number to play with and try and perturb away from this runaway solution.
But what is like the smallest dimensionless parameter?
This one is, there's several of those. So the main two are, there's G squared over kappa and G over E, where E is the gauge coupling of the vortex sector.
How big are those?
So I'm going to design it so that G is really small. These other ones are roughly the same size, but G is really small compared to the other ones. Really
small is like in absolute 10 to the minus.
Oh, 10 to the minus whatever. To start off with, I'll stick in a small number in the Lagrangian, just first to see if I can get something that exists, and then I can ask whether it's stable under quantum correction.
I mean 10 to the minus 120 or 10 to
Oh,
the
no.
minus 30,
Sorry.
or,
The small in the size of the Kaluza-Klein size. What's happening is that the radius dash dimensions in TeV units is basically kappa over G. Kappa is a length squared, and G is a length. Mm-hmm. So I'm making that hierarchy between like 10 to the 15 or something like that, between the extra dimensions and the particle physics scales. With that adjustment.
Okay, so it's microns versus
right.
The electroweak or something like that.
Right, and the numerology is that it's a standard numerology that if I can find something which goes like, if I can make the dominant contribution go like that, that's actually the size of what we see. Right now, I'm actually going to be happy if I can get you something which is suppressed by the KK scale and it has some other big scale in it, because that's better than anything else can do. But it's that's what's driving it, is that's the small numbers coming from L.
Other questions? Comments? Nothing? Okay, well, thanks a lot.
Thank you.